Okay, so calorimetry is a very useful tool to use to calculate either the molar enthalpy of the compound or the enthalpy of the reaction. However, it is not always possible to do that. So therefore, a German scientist known as Hess was saying that it doesn't really matter. If we have reactants here that we want to that are reacting together, and then we have the product here, products. And now, as we know, the change of enthalpy of the reaction is whatever is the enthalpy of the product minus the enthalpy of the reactant. He was saying that it doesn't matter how you go from reactant, let's say A, to products, let's say B. You can go straight, and this will be the enthalpy of the reaction, or you can go in another one, have a station here, and then have a station here, more probably, and then you go this way. Still, he was saying that the enthalpy of the reaction will be the same. Those are known as the intermediate reactions. What are those intermediate reactions? Are kind of halfway reactions toward the products that we want to. So in other words, I say, I call them as the main reaction, this reaction here, I call it the focus reaction. Where do you want to go? And then those intermediate reactions, I work with them with the idea as to how can I manipulate those reactions so that I am reaching the focused reaction here. So I always take those intermediate reactions and I either flip them to have the product on the reactant and the reactant on the product, or I multiply them with a certain coefficient so that I am able to cancel out compounds. And then after I add all of those intermediate manipulated reactions, I have the focused reaction along with the enthalpy of the reaction. So we will see now, but there are some things, some rules that we have to keep in mind when we are working with Hess's law. So if we have a reaction and we want to flip it, so, well, if we have a reaction, an intermediate reaction, and we want to flip it, then the enthalpy will change the sign. So if we have a reactant one, let's say A plus B gives you AB, and then you have an enthalpy here as the negative, let's suppose. What I mean by flipping it, I say that, oh, I don't want AB on the product, but I want AB on the reactant. So I go, instead of, if this is a formation, then I go decomposition, A plus B, then the enthalpy will be positive, the same value, but positive. So when I flip the reaction and I change the direction of the reaction, I change the sign of the enthalpy of this intermediate reaction that we are dealing with. And the second rule, which we even applied it when we were talking about communicating enthalpy and working with the molar enthalpy and all that stuff yesterday, is that if you are multiplying with the coefficient the intermediate reaction, then you will multiply the enthalpy with the same coefficient. So let's suppose that we have again A plus B, AB, and now I will have a number here just so that we are aware of what is happening here. Let's say 15. kilojoules. And then what I do is I multiply this by a coefficient of 1/2. Okay, then the reaction will be 1/2A plus 1/2B will give me 1/2AB, and then the enthalpy of the reaction will be negative 7.50 kilojoules. And if I'm flipping this, applying the first and the second rule, then what do I do is I go 1/2AB will give me 1/2A plus 1/2B, and then the enthalpy will be positive now 7.50 kilojoules. So the approach that we follow when we are working with Hess's law is we have the focus reaction and we have the intermediate reactions. Then we manipulate the intermediate reactions so that things are canceled out to give us the focused reaction. And then when we manipulate, so meaning that flipping, multiplying by a coefficient, then we add all of those enthalpies to give us the enthalpy of the focused reaction. Let's work with a simple example, and then we will see how to do more examples in the second part of the day today. So let's take a look now as to what is the enthalpy of the this reaction. I will give the reaction now, and then on some cases you have to write the net reaction and balanced reaction. So Br2, which is in a liquid state, Br4 in a solid state will give you in solid state. Knowing, so we are looking for the enthalpy of this reaction. No, this is the that I called it as a focused reaction. And what do we know as the intermediate reaction is that as a liquid, and with the enthalpy of this reaction of negative 146.7 kilojoules. And on the other hand, the second intermediate reaction okay, and the enthalpy of this reaction is a negative 184.4 kilojoules. This question is in your data booklet as predicting enthalpy using Hess's law. It's number 33. Okay. So again, we have a focus reaction, and we have those that, let's call it for the sake of being on the same page, as intermediate reactions. And as you see here, we have to kind of manipulate and those intermediate reactions, so that when we add those manipulated intermediate reactions, we have at the result, we have the focus reaction. So for the sake of not repeating the whole reaction, I will call this reaction as reaction 1 and this one as reaction 2. So what do you have to do when you are manipulating those intermediate reactions? You have to take them one by one, first of all, and then you have to say, what should I do are the products on the product side, are the reactant on the reactant side, or should I flip it? This will be the first one that you will see. So I see here on that's the first intermediate reaction, the WB4 is on the product side, while in the focused reaction is on the reactant side. So then what I think that I should do to the first one is I should flip it. So the first one now will be WBr4 is W solid plus 2 bromine gas or liquid, sorry. And then what should I do based on the rules that we said? What should I do to the enthalpy of the first intermediate reaction? Save it or flip it or change the sign? I have to change the sign. So now from negative will be positive 146.7 kilojoules. So when I'm done with the first one, then I say, okay, let's take a look now to the second reaction, second intermediate reaction. And then I see that on the second intermediate reaction, WBr4 is on the product side. And then when I compare it with the focused reaction, why do I have to compare it with a focused reaction? It's because this is where I want to go. This is the main thing that I want to reach. So when I see that, then I say, should I save it or should I flip it? We have to, since they are on the same side, we will save it. And then saving it means that we will even save the enthalpy, WBr46. Means that we will save the enthalpy as negative 184.4 kilojoules. Okay, now what do? Is we add them and see if we can cancel anything. And you should be able to cancel things, and then whatever is as a result of the cancellation will be the same as the focused reaction. So W being on the reactant side is canceled with W being on the product side, okay? They are in two different sides, we cancel them out. On the other hand, what do we have is we have 3 bromine on the reactant side and 2 bromine on the product side. So in this case, what do we have is 3 bromine minus 2 bromine, which will give us 1 bromine, correct? So since they are in two different sides, 1 bromine on the reactant side. So we'll have, as the after cancellation, we'll have bromine that is on the reactant side. What is left here on the reactant side is WBr4 solid. There is nothing else. Then we have on the product side only WBr6. Do you understand? Now, what do we have in terms of the enthalpy? So in terms of the enthalpy of this reaction, we'll have whatever is the enthalpy of intermediate reaction 1 plus whatever is the enthalpy of the intermediate reaction 2. So will be, I will say 1, and then enthalpy of reaction 2. Or in other words, will be positive 146.7 kilojoules plus negative 184.4 kilojoules. So the enthalpy of the reaction, the focused reaction, this one here, that we wanted to calculate the enthalpy of, will be negative 37.7 kilojoules. And this will be the final answer. Well,